So now we are going to learn about the topic interpolation and decimation. The topic specifically for the exam or as per the university syllabus is regarding frequency analysis, and we'll be learning about that topic for the time being. When we look into interpolation and decimation, the first thing that we have to understand is regarding multi-rate signal processing. We have learned about processing of digital signals in the modules so far, but what is this multi-rate signal processing? I'll give you an idea about that. So when we talk about multi-rate signal processing, first thing that we have to understand is different applications require signals in the different sampling rate. For example, if we look at our telephone system, our signal bandwidth would be around 8 kilohertz, which means our signal has to be processed to be enclosed in a bandwidth of 8 kilohertz. Normally, when we hear an audio signal over CD, we have usually seen sampling rates of 44.1 kilohertz. Now, these are just about audio signals that I am speaking about. There might be some applications which will require, like for example, digital recordings. Audio recordings could be sampled at 48 kilohertz. So these are basically regarding audio processing. Now imagine a video signal. A video signal, when it is captured, normally you know that they are converted into images, and the images are moved, or they are sequentially moved to make that look into the video mode. So basically we have some frames that are being displayed. So like you have 30 frames per second to support this concept of persistence of vision. Persistence of vision meaning to ensure that field of continuity, continuously 30 frames have to be loaded into our eye to bring in that feel of continuity. So some video standards or television standards, they require 24 frames per second. Some they require 30 frames per second. Some require 24 frames per second. So depending upon the TV standard, a source material, imagine there is a source material, and that source material contains information. Now for one TV, it will have to produce a signal of around 30 frames per second. For another TV, it will have to produce another rate of 24 frames per second. So basically what I am conveying here is a fact called multi-rate signal processing. And as per this multi-rate signal processing, what it means is that different applications require signals to be sampled at different rates, and hence you will have to modify a source signal to suit that particular application. Now, if for example, if I'm having a conversion of an audio signal that is stored in CD to a digital recording, this audio signal would be in the CD will be sampled at the rate of 44.1 kilohertz, which means that information will be containing 44,100 samples in 1 second of that signal. Meanwhile, in this 48 kilohertz scenario out here, it means there will be 48,000 samples in 1 second. So how do we convert a signal that is in 44 or having 44,100 samples in 1 second to 48,000 samples in 1 second variant? So which means this, if you want to convert this into this, some samples of around 3,900 must be added, and if you are converting it the other way around, something around 3,900 must be rejected. So I hope you're getting this concept. You have these many samples in 1 second and these many samples in 1 second. If you're converting it from A to B, if this is A and this is B, If you're converting it from A to B, 3900 samples must be added. If B is converted to A, these many samples have to be rejected, which means you are basically adding samples or you are basically rejecting samples. Now this process of adding sample is known as interpolation, and this process of removing samples will be called decimation. Process of adding samples, and this will be the process of removing samples. With this, I hope we have got a basic idea. If you look at this basic definition of interpolation or upsampling, basically it means the fact that upsampling or interpolation is a process of inserting zero valued samples between the original samples. That means what I said earlier, we are adding samples, but these samples will be zero valued, and by this what happens is you are increasing the sampling rate. You have the sampling rate conversion from 44.1 kilohertz to 48 kilohertz. So this is also known as zero stuffing, and you have got some concepts being explained over here. The primary reason to interpolate is to increase the sampling rate at the output of one system, so that another system operating at the higher sampling rate can accept the signal as input. So this is the basic concept of interpolation. Moving on, when we consider this particular scenario out here, we know that with interpolation what is implied is you have a higher sampling rate at the output side. So if we have fx and fy, let us take fx to be like 2 kilohertz and fy to be like 4 kilohertz. So the basic concept of interpolation is that the sampling rate is increased. So if you look over here, fy is equal to fx into I, and here you can see that deduce that I is equal to 2, where the interpolation factor is 2. We just saw that the interpolation factor is 2. Now we can write this equation like we already know that this particular fy and fx are related, and what we are going to do here is make a comparison of the output signal which is in the analog domain. So omega, we know the formula is given over there, 2 pi f by the sampling frequency fs. So what we are going to see here is what is a change with respect to the input signals analog frequency and output signals analog frequency with respect to the sampling frequency. So from this we know that omega is inversely proportional to fs. So we'll make a comparison. So we start off with the equation at the input side. Omega x will be equal to 2 pi f by fx, which is a sampling frequency at the input side. Now from this equation we know that 2 pi f by fx, we have this particular equation out over here, and similarly what we are going to do is we are going to try out omega y. So omega y will be equal to 2 pi f by fy. Now we know that equation with respect to fx, the relation between fx and fy, so we substitute it over here. So this can be written as fx into I. So this whole equation, that is fy is substituted with fx into I. So this whole equation can be converted to, this whole term can be combined to form wx, and this wx into I will be equal to, sorry, wx by I. So this whole equation will be wx by I, which is what is given out over here. So the implied meaning is that with respect to this sampling operation that is being carried out in the form of interpolation, where you are adding samples, what happens eventually is the input frequency will be reduced by a factor of I at the output side. So that is the point conveyed over here. Omega y will be equal to omega x by I. So I repeat, omega x will be equal to 2 pi f by capital Fx, and that we have the equation out over here. we took for a comparison omega y's equation. Omega y is equal to 2 pi f by capital Fy, and if we substitute Fy is equal to fx into I from this equation, we get this one. So 2 pi f by capital Fx can be substituted with omega x, and this omega y will be equal to omega x by I, omega or W. What we had looked at the previous slide was the fact that there will be a change in the input frequency. So we found out that omega y will be equal to omega x by I. That means whatever is the input signal at this side, it will be reduced by a factor I at the output side. So typically what happens in a now we can look at this concept of interpolation in two perspectives. One is the times perspective and the other is the frequency perspective. So as per our syllabus, we are supposed to look at the frequency perspective. But to get an idea, I'll just share this time perspective also. So here we know that in the previous case that we assumed I was equal to 2, where the interpolation factor was equal to 2, which is fx, the ratio of Fy and Fx. So what happens here is this interpolation factor m here will be equal to 2. M will be equal to 2. So what this basically means that it will be adding m minus 1 samples. If the interpolation factor is m, it will be adding m minus 1 sample. So if you look over here, you have a time graph out here where you had the signals at 0, 1 and 2. Now this is subjected to an interpolation operation and with a factor of 2, which means one 0 valued sample will be inserted between the original 2 samples. So if you look over here, you had the original sample at this position 0, which was equivalent to this one. This is available here, and then you have an insertion of a 0 valued sample at this position, which is what is shown over here. At the position 1 of the output signal, you have a 0 valued sample. Similarly, you have the original sample at position 1 at position 2 over here. Then you have a 0 valued sample inserted, and then this signal is recreated out here. So this is the process of upsampling in time domain perspective. Now what happens in the frequency perspective, that is being explained over here. So as mentioned over here, your output signal will be reduced by a factor of I. So if you look over here, if you had a signal in the span of minus B to B, what happens here is that your signal will be compressed and reduced to the span of minus B by 2 to plus B by 2, because here I is equal to 2, omega y is equal to omega x by 2. So if omega x is here is minus B, omega y will be equal to minus B by I, which is equal to minus B by 2. And here you have a sample at B, so this will be equal to B by 2. So B divided by a factor of I will be equal to correspondingly B by 2. So if you look over here, this signal is being compressed. So this span or this signal which was available from minus B to B, it becomes from minus B by 2 to plus B by 2. As a result, what happens here is that if we keep on considering the span of minus B to plus B, we can see that we get an alternate copy of this original signal in this span 2, which means we have the original signal, that is the required signal over here, and you have an alternate version. So this version corresponds to this one, and this version corresponds to the signal at this part. So you have an alternate copy of the signal which comes in the original span of the signal, which is why if you want to ensure that the interpolation happens properly, you need to use a anti-imaging filter to reject the samples. So if you look at this graph, the original graph is spanning from minus pi to plus pi. You have this signal being reduced to this particular range, but if you consider the original span, you get an alternate copy. So if you want to have this signal received properly, you need to have a filter working out over here, whereby the original output is received as a part of this process. So you need to use an anti-imaging filter after the upsampling process. So this is how the graph works. You have the original signal here, you insert the sample, and then you subject it to a low pass filter operation.